Okay, so today we are going to start a new topic, which is essentially logic. So before I talk about new topic, any questions? Is everything all right? Okay, so then let's begin. So the outline is I'll say something general about mathematics and then motivate you to the topic of logic. And then today and on Friday, we are going to talk about logic. Today we only talk about the first part, which is connectives. I'll tell you what the connectives are. Okay? And then we will talk about logical rules and how we argue in mathematics something is true. Okay. So let's begin with something really big, really general. So first I want to remind you this fact. Mathematics is different from experimental sciences. Right? Although mathematics department is in the Faculty of Science, and somehow mathematics is very, very different from, for example, physics or biology or chemistry. So in what sense? Because in the other disciplines, you can check whether something is true or not by looking at the real world. Right? For example, if you are studying biology, you make some conclusion. You want to know whether it's true or not. Then you just do experiment and see whether maybe the animal or plants show as expected. Right? But for mathematics, things are different because you cannot do experiment. Right? So everything was abstract, and it's hard to really verify. You'll see some examples as we go along. Okay, but I hope this is clear to most of you. Mathematics, the object of study is different from, for example, the object study of physics, right? So it's a big topic in philosophy. So there are actually a branch called the philosophy of mathematics. So there, people will study this kind of questions. So the first question is, what is mathematics about? Right? So mathematics is knowledge. I hope you agree with me. So it's talk about something. Now, what is the knowledge about? It's about numbers, but where are the numbers? Are there numbers in the world? So the philosophical question is, do mathematical objects exist? Right? So, for example, we talk about real numbers, or we talk about square root of -1, which is I, the complex number I. But do they exist? If you say they exist, and where are they? Is there a location? Is there a time? Are they somewhere in this world, in the universe? If you say they do not exist, then what is mathematics about? It's about something. So these are philosophical questions, right? So there's probably no clear-cut answer. People are debating and so on and so forth. But there's an issue. If you like this, and we can talk after class. Okay. So this is one question. The other question is probably related to the first one. So now, what is the nature of mathematical truth? As I said at the very beginning, in other disciplines, you can say something is true if it fits the experiment, right? You can check, but here, how do you check? Mathematics, we don't even know where it is, the thing. We talk about circle, or we talk about, I don't know, many abstract things. So how do you know it's true? is there a meaning for mathematical truth, right? And also another question is, how do you learn? Maybe in physics you learn by observation, or you learn by experiment. But here, how do you learn things about mathematics? So these are the question for fun. Okay. Now, but on the other hand, mathematics has this I don't know, the strange property. Like if something is true in mathematics, it seems definitely it will be true in the real world. Right? If somebody tells you something is mathematical truth, then very few people will doubt this is true. Right? Now, so what is the reason? What gives the aura of this infallible thing about mathematics? So one possible explanation is, the theorem is a fancy way of saying mathematical conclusion. Okay. So theorem, although it could be very, very complicated, but you can look at the theorem, you can trace back. Okay, usually in mathematics, something is called a theorem if you can have a proof. In other words, you have a sequence of statements, and the sequence is like a chain of logical, how to say? It's through a logical chain, right? So one step follows the other logically. So you have a long argument. It's like a chain. The connection between the chain are logic. So the chain on this side is the theorem you want to prove. On the other side is something called axiom. The axioms are those things which are obviously true. Nobody will doubt it, like A is A. Or you can replace the equal part by equal part. Those things are, if you don't believe that, then something wrong with you. Right? So the possible explanation is we have confidence in mathematics because we have confidence in logic, right? So that brings us to the topic of logic, and we'll see why we have confidence in logic. Okay, so these are the general introductions. Okay, so our goal is to determine the truth of mathematical statements, right? We want to argue that it is indeed true. So what are the arguments? The fancy word is called a proof. But this is not a mathematical course. I will try to avoid those formal things as far as I can. Okay, so let's look at mathematical statements. So many mathematical statements are complicated. They are compound statements. So this has nothing to do with a compound interest. So it's just a very complicated sentence. Okay, we'll see some examples in a moment. Okay, but although they are compound statements, just like a statement in daily life, you can break them down into simpler ones because they have to be grammatically correct, right? So a complicated sentence, you can break them down into simpler sentences and then keep going until you hit something really, really simple. Okay, so the compound statement can be decomposed into simpler ones and keep going, and eventually you get somewhere so simple that you cannot break them anymore, right? So let's just loosely call them atomic sentences, atomic statements. Okay, so this process of either you call it decompose, which is going from complicated to simpler ones, or if you look at the other way, you start from simple ones, you get to more and more complicated. You have to follow certain rule. It's not arbitrary, right? So the compound statement have some grammatical structures. So they were built, by using connectives and something called quantifiers. I'll tell you what quantifiers next time on Friday. So let's study only connectives. Okay. Okay, so here's some examples of mathematical statement. Okay, you can have lots of statement from daily life, but let's look at mathematical ones. So first, there's a big number. I don't want to read it. So this number is not a perfect square. So this is one sentence, but it has some structure. So it is a negation of some other sentence, right? So because the sign of the negation is this word not, right? So this is a negation of this number is a perfect square, right? So this is quite simple. Also, you can write some. In mathematics, we also encounter something like this. 3 is less than pi less than 4. Pi is the how to say? Is number associated with the circle and whatever. So pi, the number pi is between 3 and 4. Now this is a complicated sentence actually, because it says pi is bigger than 3 and pi is less than 4. Right? So this, although it's very short, actually it claims two facts. The first fact is pi is bigger than 3. The second one is pi is less than 4. Okay. Actually, pi is 3.14. And okay, some of you can memorize it for zillions. I don't know. Okay, there are films. There are stories about pi, right? Okay. Okay. So this, but anyway, so this is another example of a compound statement which can be break into two smaller ones, simpler ones. Okay. Now, also we have something like this, right? Either 2019 is a prime. Well, prime is something, I will tell you what it is. Or it is divisible by some number not exceeding 45. We don't care exactly what these things mean, but the statement have a structure. It is one statement or the other statement, right? So again, you can break them into simpler statements, okay? And maybe the most common mathematical statement are this, if then. So you can say if something happens, okay, so some funny number is a prime, or if this, then the other funny number is divisible by 3. Right? So again, this is a compound statement, and it says if, let's call this one P, if P then Q. Right? So it's of this structure. Okay. Probably the last one. The last one is the quadratic equation of this. Last time we have seen this, x squared plus bx plus c has real root. It could be one root or two roots. If and only if something happens, b squared minus 4c is bigger than or equal to 0. Right? So this if and only if is not very common in daily life, but is extremely common in mathematics. Okay. So these are the examples from mathematics. If you are, some of you are from math department, then you are seeing this every day. But other people from engineering, you probably don't see this kind of statement. Okay, so these are just examples. Now, I give you the example because I want to extract something called connectives. So those words marked with red are actually connectives, which combine two or one or two sentences to make things more complicated, right? So the most commonly used mathematical connectives are those red things, are not, and, or, if, then, and if and only if. Okay? So for our discussion, we'll use letters like P or Q or R to denote statements. Right? Just now, we have seen something like if P then Q, right? So something like this. And also we want to study the truth. So let's use two letters to denote true or false, right? The obvious choice are, let's use capital T to denote true, right? So, and use capital F to denote false. Okay, so these are quite natural, right? This is the most natural thing to do. Okay, so now, what do we care? We care about the truth of the statement, right? So what we want to do is we want to break the complicated, we want to study the truth of complicated sentences into the study of the truth of simpler ones. So the simpler ones are, the truths are given or determined by experiment. So what we are going to do is we are going to study the relation between the component of a sentence and the original sentence, right? For example, this thing denotes the negation of P. So we want to know the relation between the truth between P and its negation. So in other words, we want to break things down so that if we know the atomic truth, then we know the compound truth, the truth of the compound statement. Okay, so let's try. So for example, the negation, well, you know much better than this. So, okay. So for example, the negation of this sentence, the earth is flat, is the earth is not flat. Okay. Right, so now let's look at mathematical example. Let's say, suppose P says some number like this, 331 is a prime number, then the negation, this symbol reads as negation. The negation of P says this 331 is not a prime number, right? So this is very simple. And the truth table for this is looks like this. You can guess the meaning. So the first column stands for the truth value of P. So there are two possibilities, right? Because P is just an arbitrary sentence. It could be true, could be false, right? So the truth table like this says, we want to, tells us the relation between the truth of P and the truth of its negation, okay? So for example, here, when P is true, the negation, okay, of course you know, is false, right? So when P is false, then the negation becomes true. So this is the connection between the truth value between P and not P using the table form. We are going to see more complicated table than this, but more or less it has this structure, okay? This is, I think, it's very simple, so no need to spend too much time. Now let's look at others. So we have 5 connectives to study. Most of them are straightforward, but let's just go through it so that we make sure we know everything. Okay. So the next one is called conjunction. So actually, many people read it as and. Okay. So the symbol of this is this wedge. So we use P wedge Q, or we just read it P and Q, to denote the compound sentence, the sentence P and sentence Q. Okay. The truth table is very simple. So now this time, the and connect 2 sentences, right? So the atomic component are P and Q. We are interested in finding the truth value of P wedge, P and Q, okay? Well, the different combinations of 2 letters are like this. So both of them can be true, both can be false, or the first one is true, second one is false, or the other way. There are only 4 possibilities. right? So now P, okay, if both of them are true, then P and Q is true, right? And if one of them is false, then P and Q is not true anymore, right? Because if you want to say the AND is true, it must be both sides are true. So if one side breaks down, then the compound is not true anymore. So only in the case that both P and Q are true, this compound is true. In all other three cases, they are false. Right? Again, there's no it's quite clear, I think. Let's look at some examples. So fix a number A. Suppose P says A is less than 4, and Q says A is bigger than 1. Now, what is this compound, P and Q, P wedge Q? So it says, okay, as you expected, P, which is A less than 4, and A is bigger than 1. Right? So it claims this number is less than 4 and at the same time is bigger than 1. We often write this as just like this, right? 1 is less than A, less than 4. Right? We have seen this in the example pi. Okay, now in natural language, in daily life language, the things are more exciting. So there are, you can use different words to say the same thing, or you can use the same thing to mean different meaning, right? So, but mathematics is trying to be clear and precise. So mathematics will cut the fun out, right? So anyway, so in everyday language, you can use other words to say the same thing, like and. The textbook gives this example. The textbook says, look at this sentence. So he's rich but unhappy. So it claims two things, two facts, right? So this is actually equivalent to the compound, he is rich and he is unhappy, right? But in daily life, because here there's a turn of the meaning, right? Usually people guess that if somebody is rich, he should be happy, but here there's a twist. So instead of using and, you use but to indicating that the subtle, how to say, to indicate the unexpected result. Right? But here, we are not talking about linguistics, we just talk about mathematics. So in mathematics, everything was clear, it's just we follow this rule and it turns everything to end. Okay? There are other examples. The textbook gives you other examples, but like as well as or both and. So in daily life, you have many, many different ways of say the same thing. But we are clear what we are talking about. Okay. Now, the next one is or. Okay. So we use P, it's like a V. This P or Q to denote the compound P in English is OR or Q. Okay. Now the truth table, okay, again, 4 possibilities of the combination of P and Q. The or, P or Q is true, it turns out to be like this. Okay, so for example, let's look at the 2 rows in the middle first. So if one of them is true, then P or Q is true, right? Because you said either this or that, right? So there's no difference between mathematical meaning and the daily life meaning. The last row also there's no difference. If both of them are false, then P or Q is false, right? Now the first one, in mathematics, we say if both P and Q are true, then P or Q is true. This is slightly from daily life use. Okay, so we'll talk about this at the last item. So let's look at some example first, then I'll explain more about this difference between daily life and mathematics. Okay, So let's look at some examples. So again, fix a number A. Let P says A is less than 4. Q says A is equal 4. Okay, so there are two statements about A. And then what is P or Q? P, V, Q. P or Q says A, okay, less than 4, or A is equal to 4, right? And we often write in the shorthand says A is less than or equal to 4. Okay, so this is clear, right? Now to test whether you understand this or, let's ask ourselves the question: is 3 less than or equal to 4 true? Somebody says it's not true because it cannot be equal. Do you agree? You are right, it cannot be equal. But to understand the truth of or, there are two parts. As long as one part is true, the whole thing is true. Right? You see here, right? So although A cannot be, 3 cannot be equal to 4, but 3 is less than 4. So therefore, the answer for the first question is actually true. Right? You have to follow the table, truth table. Okay. Now, it's even less obvious. Okay, is 2 less than or equal to 2 true? Ah, no, good. Yes. So now you learn. Okay. So yes. So this 2 less than or equal to 2, actually, there are two possibilities, right? So the first part says 2 is less than 2, but this is nonsense. 2 is not less than 2, but 2 is equal to 2. So this is true because of the second second sentence is true, right? So the or is still true, right? So this is okay. So the remark here is this or in mathematics is called inclusive, meaning it includes the case both of them are true. Now, in daily life, the or sometimes means exclusive. For example, you say either you go or I go. It probably means if you go, I don't go, right? So if I go, you don't go. But in mathematics, it's not exclusive. If both of us go, it's okay. It's still true. Okay, so this is okay. In mathematics, you just choose one, make everything precise, right? No ambiguity. We have to draw the line. So we draw the line this way. Okay. Okay, so questions? It's fairly natural, right? Now, we can talk about some sentences have the same meaning, or they are equivalent. They are logically equivalent. So the definition of this is two statements are called logically equivalent, or very often we just say equivalent, if the truth value in corresponding rows of their truth table are identical. I'll show you example in a second. Okay. So, for example, P or Q and Q or P are equivalent. So if we draw the truth table, now let me try to draw it here. I don't know how to do. Did I? Why it is? Why it doesn't show up in the place I? Okay, so I'll draw all these truth tables in one shot later. Use the visualizer, but I think you know what I'm saying. I don't know why the annotator when I touch the screen doesn't show up. I don't know what's going on. Maybe during the break somebody can teach me. Okay. Anyway, so let's keep going. Okay. So, so indeed, if you draw the truth table of 4 rows, and then you look at the truth value of the corresponding row, the truth value of P or Q and Q or P are the same, are exactly the same. So therefore, they are equivalent. Okay. The same for the AND. This is easy. Oh, some people use this 3 strokes for equivalence, but we are not in mathematical logic, so we just use words, equivalent. Okay, so why do we care about 2 equivalent? Why do we care about equivalence? The equivalence statement, we can think of them as a single one, right? So for 2 equivalent statements, establishing the truth of one of them also establish the other, because they have the same truth value. So if one is true, the other one is true, right? And vice versa. So for equivalent statement, we don't need to do things twice. We just do it once. Okay. So it is helpful sometimes. Okay. Now, just now the example we have seen are very, very simple. You just P and Q or P or Q. Suppose you have the sentence, the structure is more complicated. Sometimes you have to parse them in the right way. So you have to make sure that it means what you mean. So in other words, sometimes you have to use bracket. For example, let's look at this. Let's look at example 1. Okay. So I want to say that P or bracket Q and R, and this bracket, if I put P or Q first, and then conjunct, then take the AND with R, these 2 sentences, these 2 statements have different meanings. Okay, so let's first make sure this, right? So I want to say these 2 items are not equivalent. So how do I convince you it's not equivalent? So I'll give you a assignment or a value of PQR where these 2 guys have different value. Okay, it's quite easy, right? So for example, if I give you P is true, R is false. I don't care Q even. So if P is true, R is false. The first one is, okay. The first one is true, right? Because when P is true, it or anything is true, right? Now let's look at this one. Suppose P is true, R is false. Now, if R is false, then no matter, I don't care what is the first one. The whole thing is always false. So therefore, the first one is true, the second one is false. So they are not equivalent, right? So why do I say this is an ambiguity? Suppose we don't have bracket. Suppose you just write P wedge, the V, Q, wedge, R. Then the meaning is not fixed. We don't know whether you mean you bracket P or Q first, or you bracket Q and R first, right? So in case that something, the meaning is not fixed, you have to use bracket. Once you use bracket, everything was fixed. Okay. So this is one example. Okay, I will not go through all the examples, but you know what I mean. And then we look at the relation between the 3 connectives we have introduced. So we have negation, we have and, we have or. So now let's see how do we take negation of P or Q or P and Q. This is well known. There's a law called De Morgan's law. De Morgan probably is a Scottish or so it's somewhere there. He's Scottish. He's a Scottish mathematician logician, and he has done this work. Okay. So so De Morgan's law says, if you negate P and Q, right, this is equivalent to you do negate P and negate Q, but the AND become OR. You have to flip the AND and OR. Okay. The same for the other way. Suppose you negate P or Q, the result will be you negate P, negate Q, but now you have to connect them in the different way. You have to connect them by AND. Okay, so this is called De Morgan's law. Another simple law says if you take double negation, then you get the original P. Double negation is the same as the original state. So double negation and P are equivalent. You can draw truth table. It's quite obvious. Okay. All right. So let's look at some examples of De Morgan's law. But this I think is pretty easy. So let's just go through it. So this is something from daily life. I took it from the textbook. So we want to negate this sentence. He is rich and powerful, right? So when is the statement false, it means you take negation. Okay. So the negation of this is, okay, so is P and Q. So when you take negation, you have to negate P, negate Q, but you have to change the AND to OR. This is the De Morgan's law, right? So the answer is, okay, he is not rich or he is not powerful. So this is the negation, okay, right? Okay, so now let's look at mathematical examples, right? Again, we fix the number A. Suppose we have this sentence, either A is 0 or A is 1. We want to negate this sentence. So what is the negation? So we have to negate both components, right? So A is 0 become A is not 0. A is 1 become A is not 1. Now, the important thing is, by De Morgan's law, the OR you have to change to N. Right? So the negation of this sentence is A is not 0 and A is not 1. Okay. Now another exercise is the negation of this 3 less than A less than 4. So A is between 3 and 4 is, okay, so you have to negate 3 less than A. So the negation will put A is less or equal to 3, right? So you compare A and 3. If A is not bigger than 3, then it is to the left-hand side of 3. So it's less or equal to 3, right? Now, the same reason for if the A is less than 4, if you negate it, it becomes A is bigger than or equal to 4. So imagine the numbers lining up on a line like this. So if A does not show up to the left of 4, then A must show up either at 4 or to the right of 4, right? So if you negate this, A less than 4, you get A is bigger than or equal to 4. But here, the connective is AND. By De Morgan's law, you have to change it to OR, right? So this is examples of De Morgan's law. Okay. So, and then we look at some statements which are always true and some statements which are always false. So a statement which is always true for all possible truth value combinations of its component is called tautology. It's a fancy word, probably from Greek. So tautology means always true. No matter what happens, it's true forever. Now, the opposite is it is always false. So the sentence which is always false is called a contradiction, because a contradiction is never true. It's always false. Okay. Can we have some examples? Okay. Now, the negation, okay, not P or P. This is a tautology. It's always true. Right? Let's try. Suppose P is true, and then the whole thing is true because of the second disjunct, right? Suppose P is false, well, then the negation will be true. The first disjunct will be true, so the OR is true. So no matter P is true or false, the compound is always true. So this is an example of a tautology. Now, by the same reason, this is always false. I will leave it to you. Okay. Now, this is the fun part. I guess most of you have seen this, but suppose you haven't seen this, then this is the most interesting part among these connectives. So we want to study the meaning of if-then. Okay. So we use P arrow Q to denote the compound if P then Q. So the daily life reading is from P you can derive, you can get Q, right? You can conclude Q, right? Okay, so now what is the truth table? So the truth table of P, let's read that P arrow Q, let's just say P arrow Q is set in this way, right? Okay, so suppose both P and Q are true, then this arrow is true. This I think everybody agrees. From the correct thing you get correct things, then probably is right? So this is true. Now the second part, suppose P is true, but Q is false, and then this arrow is false, right? Because from correct things you get something wrong, then it must be you have something wrong, right? It's not the fact, but you. So the second row again is no controversy. But the last two is a bit need some explanation. So the last two says, suppose P is false, and then no matter what happened to Q, the whole conditional is true. This is a little bit against your intuition, because you would think that P arrow Q means I look at P, somehow I analyze P, and then somehow I will get Q, right? But if P is false, then this reasoning doesn't work, right? So you would think that maybe you would think this shouldn't be true, but in mathematics we set it to be true. Okay. First, are you with me for this truth table? The next slides, I'm going to try to give you some reasons. Everything in mathematics must have reason, right? So next slides, I'll give you some reason why mathematicians set things up in this way. Okay, so you are with me, right? You have to memorize this. So P arrow Q, the only case that P arrow Q is false is P is true, Q is false. Right? Okay, so this is the important message. Okay. Let me ask, how many of you haven't seen this before? This is the first time you have seen this. Wow, okay. So then the next slide is important for you. I want to convince you that there's a reason to do this. Okay. So let's look at some explanation. So I'll give you two explanations here. Then after a while, I'll give you one more. Okay. And if you are still not convinced, I'll tell you something else. Okay. Okay. So let's try. So the question is it reasonable to set P arrow Q is true when P is false? Right. So just now, I think nobody is going to question the first two rows. First two rows are very natural, just fits our intuition. So the only questionable part is the last two rows, right? So let's look at them. So is it reasonable to set this? Well, let's look at a daily life example. So I think Singapore government did make this promise. Says if you get an Olympic medal, gold medal, and then the government will give you $1 million, right? I hope this is correct. Okay. So it's a if-then, right? If-then. Now, when do you think this is true? The sentence is true means government keep this promise, right? He is telling the truth, right? When do you think it is false? That is, the government did not keep his promise. Okay. So, okay, if you get Olympic medal, like the swimmer, right? Then the government give him $1 million. And then, of course, it's true. Government keep his promise, right? Now, suppose people like you and me, I don't think any of us have get an Olympic gold medal. So, and we didn't get the $1 million. Are we going to complain? No, right? It's still true. Right? The government didn't break his promise because we didn't get Olympic medal, right? So now when the government fail us, when do the government fail us? Only when you get the gold medal in Olympics, maybe next time, and the government didn't give you 1 million. Then this is the case. This is the only case where the implication or the arrow is false, right? So this is a daily life explanation. Of course, some people in the audience are very smart, can give me some examples in which case it doesn't, but okay, it doesn't sound very right, but anyway, this is, how to say, this is just an explanation. I'm just telling you that there's a reason. Okay. Because we have to set the rule. We have to give a precise meaning of this if-then, right? So there are many, many choices, but we have to make it precise. So that's the way we define, we set the rule. Okay. Now the second part is I'll show you a different reason. So the reason says this. Let's consider this truth table. Before we consider truth table, why do I look at this particular statement? So I want to convince you in our daily life, this is always true. Why? Because if you believe P and Q, actually you believe more than Q. Right? You not only you believe Q, not only you think Q is true, you think P is also true. In addition to the information Q is true. So therefore, this P and Q always implies Q. This is fairly straightforward, right? If you think P and Q is true, certainly you think Q is true. So therefore, this implication is always right. Is this okay? Okay. So now I want to convince you this has something to do with the arrow. Give me a second to set up this because I don't know how to write on the. Can you hear me? Okay, so so this part I leave blank for a second. Can you read from the back? Okay, good. Okay, so the combination of these are right. So this and the only case when the and is true is both of them are true. So the other guys are F, F, F. Now before I draw this truth table, I've said this is all the reasonable reading of this P and Q, arrow Q is always true, right? You all agree with me before I come to this visualizer, okay? So this part should be always true, okay? Okay, so now look at, this is P arrow, P and Q, arrow Q. So let me just copy the Q here. So the truth value Q is TF, right? I'm just copying this one to here. Okay, so now look at P arrow Q, arrow Q. Look at this line. And the third line. So the second row says F arrow F should be T, right? The third row says F arrow T should be also T, right? So we have a choice, right? If you want to keep this one is always true, then you have no choice. You have to set F arrow F to be T, and F arrow T also T. Right, so again, this is some reason. Okay, so now let's go back to the proper slides. Okay. I hope this is clear, right? So this is a. Okay, so in daily life, we always have different words for the if-then. So we'll say suppose, assume, given P, then Q. Right? And also for the conclusion part, you have these several choices of words. So it's that it follows. So, okay, suppose P, it follows that, or thus, or therefore, or hence. So you have all these words, but it means then. Okay. And this is maybe too mathematical. Let's move on. So in daily life or in mathematics, sometimes people also use only if, and this is quite confusing. Okay, so the compound P only if Q means Q arrow, means P arrow Q. This is different from P if Q, right? Because P if Q means if Q then P. So only if is the opposite of if. Okay, so look at some example. So only an honest person can be the president. Maybe somewhere in the world it's not the case, but that's not our concern. Okay, so in other words, one can be the president only if one is honest, right? So what does it mean? It doesn't mean every honest person is president, right? It doesn't mean if somebody is honest, then it is president. It means the other way. If somebody is president, then he is honest, right? So this is an example illustrating this. Okay. Right, so again, for arrows, the bracket is important. For example, let's say, if you just write this, P arrow, Q arrow, R, this is ambiguous. It's very vague because do you mean you first do P arrow Q or you first do Q arrow R? And these two are not equivalent. So I don't have time, but I leave this for you. You can draw a truth table and see the difference. It's quite easy to see. So in other words, don't write this. If you write things like that, you have to add bracket. Okay, so I'll do this and then we take a break. Okay. Okay, so like I did before, we have negation and or. And now we have negation and or and arrow, right? So now we want to look at the relation between them. So it turns out you can express this arrow by using negation and or and negation and and. So the claim is the following three expressions are equivalent. They have the same truth table. Okay. Let's take a break, and during the break you can draw the truth table and see whether this is true. Okay, so we take 5 minutes break. Okay. Okay, so just now I got some questions. One question is the reason for this table. Okay, I spent all my attention on the last 2 rows, but the question remains on the first 2 rows. So what do you think? Suppose I have P and Q. I say P derives or P if P then Q. If both of them are correct, should I give this right? So if from true and true from true I derive true, right? From truth, if then means from here I get, from P I get Q. If P then Q, right? So from, assume I have P, and then I do something, I get Q. From something true, I get something true. This shouldn't be a surprise, right? So this, I was trying to say that from truth I get truth is this kind of reasoning is correct. It's not fishy. You may consider the meaning. You may read into the meaning of P and Q. You want to say maybe this is true only when P and Q are related, but that's a different concern. So here we didn't consider whether P and Q are related or talking about same thing. We are just say if from a true fact I derive a true fact, and then the derivation is reasonable, is not too bad. I think, does anyone have better explanations? Because if I set this to F, it's absurd, right? Because from true things I get true things, then this is not correct. Then this is even worse. This is even more surprising. Is it? Let me make one more last attempt to explain the first row. Okay, my last attempt. Suppose we hate this T. We want to change it, only one choice, change it to F. And then I think most of you will be angry at me, right? So from true I get true. You say this is not correct. Then this cannot be F, right? Definitely it should be true. Is this okay? Okay, if you have better explanations, please talk to me so that I can repeat your argument to your classmates. Okay. Now move on to the second row. If I start from something true, I get something false, then this derivation, this line of reasoning is not valid, right? It's false. It's not correct. I think this is very natural, because if P then Q, you want to say we derive from the correct, from a true statement I derive, if from true statement I derive a false statement, then my derivation is wrong, right? I'm crazy. Right? So therefore, the if P then Q should be false. Is this all right? Okay, so let me know if you are still confused. And okay, so let's move on. Okay. Okay, so now let's treat this as an exercise on truth table. Because some expert didn't fix my annotator, so I have to rely on the low-tech. Okay, so I have three things, right? P arrow Q. This is not P or Q. The last one is very complicated. P and not Q. This. Right, so I have, so the combinations are right, so we have this. Now, by the table we have seen a few minutes earlier, this is T, this is F, this is T, this is T. Okay? Now, how about this one? Okay, so we have negation of P and we have Q. As long as one of them is T, Okay, so first, the first row should be T because Q is T, right? So the OR is T. Now here, the third row is also T because of Q. Okay. Now how about the second and last row? So in the second and last row, so what do we have? So the second row, negation of P become false. So false or false is false. In the last row, the negation of P become true, right? So true or Q, so this is true, right? So these two have the same truth table. So they are equivalent. Okay. Now, I guess I leave this to you. In the end, it will be the same. I have to move on, so sorry. I think. Oh, you can, okay. Some of you are seeing, okay. So let's move on, okay. Now, why do although I didn't explain the third one, this one actually helps us to take negation of this arrow. Okay. So the next topic is, logically, if I take negation of if-then, what does it mean? Okay. So this example says the negation of this arrow is equivalent to P and not Q. It's hard to use examples, but if you agree that 1 and 3 are the same thing, the negation of 1 should be the negation of 3, right? Because if they are the same, then you can take negation on both of them. Now, the negation of 1 is not bracket P arrow Q. Negation of 3, okay, you start with double negation. But we have seen that double negation can be cancelled. So if you take negation of 3, you just get this P and not Q, which is exactly this. Right? You can think of other reasons, but at least actually this is equivalent to that. In mathematics, this was used very often because, okay, so the negation, for example, let's say the negation of if x is not 0, then y equals 0. So it's negation of if P, then Q. Now, what's the negation? According to this formulation, you keep P as the same. So this is x not 0. And this part become and negation of the second one, y is not 0. Okay, so this rule make us, how to say, mechanic. Okay, sorry. Usually when you take negation, you have to think of meaning and so on and so forth, right? But somehow in mathematics, if you memorize certain rules, and then taking negation, you can just follow the rules. You can just manipulate the symbols blindly without really see the reason. So this somehow help us. Actually, computer does this. Computer probably do not understand what it says, but it can follow the rules, change one sentence to the other. But the result is correct. So, okay, so this is how to take negation of if then. And then there are a few related statements. So the statement Q arrow P is called the converse of P arrow Q. Suppose we have P arrow Q. If I flip this, it is called converse. Q arrow P is the converse of P arrow Q. Okay. For example, suppose P says A less than 1, A is less than 1. Q says A is less than 100. Let's say, what is P arrow Q? It says if A is less than 1, then A is less than 100. Right? So this is correct. Right? Now, how about its converse? The converse says if A is less than 100, then A is less than 1, which is not correct. Right? Because 99 is less than 100, 99 is not less than 1. Right? So they are not equivalent. And something related to this, if you add a negation to this if then, okay, the statement of not P arrow not Q is called the inverse of P arrow Q. Okay. Well, for example, P and Q are as this. So P arrow Q is the same, right? Is if A is less than 1, then A is less than 100. Now, how about its inverse? So it says if A is not less than 1, then A is not less than 100. Right? So the inverse of this says if A is not less than 1, then A is not less than 100. But this is false. Right? Again, 99 is an example. So in the first year of mathematics, we often label some common mistakes in logic. This is one of them. So it's called converse error. So from the example above, you know that a statement and its converse may not be equivalent. Right? Like A less than 1, if A less than 1, then A is less than 100, and the converse is different, right? So if you confuse about the two, if you confuse some statement with its converse, and then you are committing an error called converse error, right? That's very natural, right? Because the mistake is you use its converse as the original statement. Okay. So on the textbook, it gave a daily life example. It says this: if it rains, then I bring an umbrella. So usually this is logical. Right? If it rains, I bring an umbrella. Now, if you think this sentence is the same as if I bring an umbrella, then it rains. You are committing a converse error. This is a funny sentence, right? Whenever you bring an umbrella, go out, then it rains. Anyway, but let's care about more on mathematics. Okay, so here's an example from mathematics. Okay, look at this. One statement says, if m and n are even, even means divisible by 2, is a multiple of 2, like 2, 4, 6, these are even numbers. If you have two numbers, both of them are even, like m is 2, n is 4, right? And then the product, m times n, is even. Okay? So this is a statement, and it turns out to be a true statement, right? Now suppose you made a mistake. Suppose you commit a converse error. That is, you think the converse is true. Say, if m times n is even, and then m and n are even. Now, this statement, the second statement, is false, right? For example, m is 3, n is 2. Then m times n is 6, which is even. But m is 3. 3 is not even, right? So if you somehow confuse these two, you are committing a converse error. You can compose an inverse error. You can call something inverse error as you can imagine, right? If you confuse the original statement with its inverse, then you are committing an inverse error. Okay. So, but the last possibility turns out to be correct. So there's something called contrapositive. So the meaning of contrapositive is this. The statement, you take negation on both of them. At the same time, you flip. Let me slow down. So converse means flip. You suppose you start with P arrow Q. Converse means Q arrow P. So converse means you flip the premise and the conclusion, right? And inverse means you just take negation. The contrapositive is you do these two things together. So the statement of not Q, arrow not P is called the contrapositive of P arrow Q. Okay? Now, it turns out the statement of P arrow Q and its contrapositive are always equivalent. Again, you can draw the truth table. You can see there. Yeah. So for example, again, use the example we used before. Suppose P says A less than 1, A is less than 1, Q says A is less than 100, right? So P arrow Q says if A is less than 1, then A is less than 100. Okay, so this is correct. What is the contrapositive? It says if A is not less than 100, then A is not less than 1. This is correct, right? So in other words, if A is greater than or equal to 100, then A is greater than or equal to 1. This is certainly true, right? Because it's even bigger than 100, certainly it's bigger than 1. Right? So, okay, so it turns out P arrow Q and its contrapositive are always equivalent. And the converse, Q arrow P, and the inverse, not P arrow not Q, they are also equivalent. So among the four combinations, original one, contrapositive are equivalent. Converse and inverse are equivalent. The others are not. Okay, so the last one, the last connective we are going to introduce. So we use P double arrow Q. So the fancy word is biconditional. Conditional means single arrow. Now suppose you have the arrow both ways, it's called biconditionals. Okay, so we use P double arrow Q to denote the compound P if and only if Q. So this is, we introduced P if Q. We also introduced P only if Q, right? So actually this is indeed double arrow. Okay. Okay, so the truth table of this goes like this. if the value of P and Q agrees, and then this double arrow is true. So for example, P is T, Q is T, then P double arrow Q is T. The same for F. If P is F, Q is F, the truth value agrees, and then the biconditional is true. The other two cases are false. If the truth value of P and Q are different, and then the double arrow fails. This is not too bad, right? This is easy to believe. Double arrow means they are the same in some sense, right? So when they agree, then the double arrow is true. When they disagree, the double arrow is false. Okay. You can think of this because it's called if and only if. So this is if, right? P if, right? This is only if, right? P only if Q, and then this is P if Q. So this is only if, this is if. So if and only if. These two are equivalent. Okay. I know you don't have time to digest, but you can draw a truth table afterwards. Okay, so if and only if very often is, we shorten it as IFF. It's a wrong spelling, but it stands for if and only if. Well, I didn't talk about sufficient and necessary, so let's skip this. Now, here's another explanation of why we set P arrow Q when P is false. The whole thing is true. Okay. Let me say what I'm trying to do. I'm trying to explain why it's reasonable to have, when P is false, no matter what happened here, we have to give true here. Okay? Right? So this is what I want to do. So how do I do it? Okay, suppose you hate TT here. Give me your favorite solution. Well, you have 4 possibilities. TT is the one I propose you don't like, right? So there are 3 other possibilities. One is TF. Okay, suppose let's put here T. The star is T. The double star is F. Okay, is this a good arrangement? Well, if you put here T, put here F, this looks like exactly like Q. You are saying if P then Q has nothing to do with P. You just look at the value of Q, just copy it. This is not satisfactory. Are you with me? So, okay. Now, another possibility. This, just now I tried TF, right? Let's try FT. So the single star is F, the double star is T. Right? Now, what is the truth table? So this guy is F, this guy is T. This is exactly the double arrow. Right? Double arrow record 2 things agree or disagree. Now, the single arrow should be different. Well, hopefully you buy this, right? So therefore, if I put F here, T here, I get double arrow. Double arrow, well, should be a different connective. Okay, so that's ruled out. There's only one more choice. This is F and F. Okay, is this familiar? Suppose I put here is F, here is F. What is this? Okay, so TFFF. This, suppose the last column is TFFF. This is conjunction. This is AND. Of course, you don't want if then is the same as AND, right? So the other choices are not good. Okay, so this is explanation. It's not, how to say, not very, it's just explanation. You buy it, you buy it. You don't buy it, fine. Okay. All right. So I still have a few minutes, so let's continue. So now, okay. So I introduced the 5 connectives. Okay. So you know that the relation between simple truths to complicated truths, right? So far we know that. Now the next thing is to say the derivation, because I said you have to follow logic from one statement to the other, right? So here is the logic. How do we derive? How do we really do mathematical argument following logic? So here's a strange sounding model exponent. It says this. So I think intuitively it's very clear. Suppose you have P arrow Q and you have P, you can get Q. This is almost like the syllogism, right? If P arrow Q, if P then Q, you have P, then you have Q. This is the simplest form of derivation. Derivation means reasoning. Right? I hope you agree with me for this reasoning. Right? We set it as a rule. So in other words, suppose I have P arrow Q. If I have if P then Q, I also have P. And then I can derive, I can get Q. Right? This is the rule of logic. Okay. So if you don't remember, it's fine. It is called model exponent. It's Latin. Okay. So the important thing about the rule is the rule will keep truth. If P, so just now we say from P arrow Q and from P, I can derive Q, right? The model exponent says exactly that. P arrow Q and P, we get Q. So it's P arrow Q and P, we get, if this is true, then we get it, right? So is this reasonable? Well, this is reasonable because this is tautology. This is always true. If it's always true, I can use it as a rule. Okay, so I think this is believable. Right? Okay, so you can draw a truth table. Actually, we don't need to draw a truth table every time. So let me give you a shortcut. Right? Suppose I want to convince you this is tautology. What is the shortcut? I want to convince you this is always true. Okay. So let's try very hard to make it false. Okay. Try our best to make it false. So here, so let's write F here. All right. I want to make this thing false. So this is what I hope. I want this F. There's only one way to make an arrow F. That is, this side I have to give true, this side I have to give F. Are you with me? So I want to make the arrow F. There's only one way, if you remember the truth table. There's only one condition which this happens. This is this side true. This side I write it under T because it's a conjunction. And this side F. This is the only possibility that the arrow is false. Is the premise is true, the conclusion is false. Okay? So we have no choice. We have to give Q false. Right? Suppose we want to give the whole thing false, we have to make Q false, and we have to make this end true. Right? You are with me here. Okay, now let's look at this end. Now, how do I make this end true? There's only one way. Both of them are true. Right? So in other words, this P I have to give it true. This arrow I have to give it true. This is the only way. Okay? Now, how do I make this true? So now I find out the exact value of P and Q. So Q has to be false. P has to be true. So now look at here. P has to be true. Q has to be false, right? So this is, we just concluded. But if P is true, Q is false, then this arrow is F. Is not true. So there's impossible. Let me repeat what I'm doing here. So this part is I'm trying my best to make this one false. Right? Then I'm analyzing under what condition this can happen. Now, it turns out we are quite lucky. It is easy to argue in this way. So the only way to make this arrow F is this guy is true, the thing after arrow is false. Right? That's why I wrote T here, F there. Okay, so in other words, Q has to be F. If we want to make the whole thing F, Q has to be F. Now move on to this T. The only way to make the conjunction T is both of them are T. Right? So in other words, we have no choice, but we have to give P T. Okay? Now combine P equal T, Q equal F, then this part become F. But we need this part to be T to get this F. So impossible. We try our best, we fail. So this is always true. It's impossible to make it false, right? I think this is easier than drawing the truth table and doing things. Okay, so this is an example of a rule, which is the model exponent, and the explanation is the rule will keep the truth, preserve the truth. I'm saying this because at the very beginning I'm telling you if we follow the logical rules, we cannot go wrong, because we start from something true. If we follow the logical rule, we always get truth. From true, we always get true. So therefore, mathematical statement is reliable. It's because of the property. Now, you may have other logical rules. For example, if from P you get Q, from Q you get R, and then from P you can get R. This is, again, quite simple. We use it all the time. So you can justify this by saying this is a tautology, right? If you have P arrow Q and you have Q arrow R, then you can get P arrow R. This thing is always true. Again, you can try, right? Suppose you want to make this guy F, this has to be T, this guy to be F, and you can play the same thing. And hopefully, it's easier. In case you don't have easy solution, just draw the truth table. So it's tedious, but it's always works. Okay. It always works. And something else. Okay, so this is the last item for today. I'm sorry to keep you here for another 3 minutes. Okay. So I want to tell you an important argument in mathematics. It's called proof by contradiction. So since just now, lots of you didn't see connective before, so you probably haven't seen the proof by contradiction before. But never mind. So proof by contradiction is a very powerful way of proving or arguing, right? So let's look at an example. So today I give you a very simple example. Next time we'll see some classical examples. Okay. Okay. So let's look at this. So I don't read the numbers. It's a huge number. So the claim is this number is not a perfect square. The meaning of perfect square is it is some numbers square. It's okay. N times n is n squared. So the meaning of this is this funny number is not equal to n squared. It's not equal to n times n for any n, for any number n. Okay. Okay. So this is too long, right? I don't know what it is. So just call this number z. This is a z. Okay. I want to convince you that z is not some other integer's square. Okay? Okay, of course you can try to punch your calculator. So from 1, 2, 3, you try everything until this funny number. And you can try everything. Then if nobody square equal to z, then you win, right? But that's not mathematics, right? That's only for machine you can do this. So we don't try this brute force. So then the reasoning is maybe this z is a perfect number. Let's say this is t squared. Let's see what happens. Okay. So suppose z is t squared. What can we say about t? Well, first you can see that t has to be an odd number. Just now we say even number. Even number is multiple of 2, right? So even number square is also even, right? So if you are multiple of 2, you time yourself against multiple of 2, right? So even number square is even, but if z is t squared, t cannot be even, because if t is even, z would be even. So t has to be odd, right? So the because is what I said, because an even number square is even. Okay. Now, what is the meaning of odd number? If you write an odd number, the last digit has to be 1, 3, 5, 7, or 9, right? Odd number is like this. Okay, so then if you square it, the last digit of 1 is, your square is still 1. But if you square 3, you get 9. If you square 5, you get 25. But we care about last digit, so it's 5. Same. For 7, the last digit is 9. If you square, 9 is 81. The last digit is 1, right? So if you square it, t square should end with either 1 or 9 or 5. Okay. Okay. So if you really look at details, you can do something like this. Being an odd number, it's the last digit. Let's say last digit is 1, so it means it's 1 plus a multiple of 10. Right? If the last digit is 1, it's a multiple of 10 plus 1. Okay. 31 is 3 times 10 plus 1. Right? Okay, now if you square it, you get another multiple of 10 plus 1. It means the last digit is still 1. But I think this is quite okay. If the last digit is this, then square, the last digit of the square are that. I think this is quite okay. Okay, so now we know how to solve the problem. So the problem is like this. Suppose the given number z is a square of some odd number, say t. So t has to be of this form. T is a multiple of 10 plus r, where r is odd. It's 1, 3, 5, 7, 9. Okay? And then if you square it, you get something like this. And this part doesn't have anything to do with last digit because it's multiple of 10. So it is of higher digit. Right? So the only r square can affect the last digit. But we just now we saw r square will be 1 or 9 or 5. But however, this funny guy's last digit is 7. Did I type it right? Is it 7? Ah, good. So it's 7. Okay, I don't care what happens in between. Anything end with 7 won't be a perfect square. Right? Okay, so hence z is not a perfect square. Okay? Okay, so to wrap things up, okay, let's take a look at this so-called proof or argument. So we begin with this. Suppose that z is a square. So this is the opposite of what we want to show. Right? I want to show this guy is not a square, but somehow I say, suppose it is a square. Right? And then so the comment is, the advantage of this is it gave us something to work on. Right? So suppose it's not square, then we can say something. So we start from there and do our things. Okay, so then we keep so suppose it is a square, and then we try to reasoning. Deduce is a funny way, is a fancy way of saying reasoning, right? So if it is a square, then z would end with 1 or 5 or 9. But that is a contradiction. They contradict to the fact z ends in a 7. So we assume the opposite, and then we get something wrong. We get something contradictory, right? So because of this contradiction, we have to admit the assumption is wrong. Right? Our supposition is wrong. So this kind of argument is called proof by contradiction. You assume you want to show P, you assume not P, then you get something wrong. Where is the source of something wrong? It must be because I assume not P, right? So therefore P has to be true. So this is a strange argument. Right? So this kind of argument, assume what you wish to prove is false, and then get a contradiction, is commonly employed in mathematical proof. So this is called proof by contradiction. Okay. So so next time you'll see some more complicated proofs. But it's classical. I believe everybody should know. So we are going to show square root 2 is irrational. Okay. Okay, so sorry for being late. That's all. See you on Friday.